So we begin the course with Chapter 1, Density-Independent Population Models. So there's a few terms that we're going to define to start off the chapter, but the focus is going to be really on that second half of the title, population models. We're going to be looking at using Excel to kind of estimate where a population of a species, or whatever it might be, where that will be in future time. Usually on a scale of months, but depending, it might be years. So let's begin with some definitions. So we start with mathematical models, which is a large base of this course. The whole point is models for life. And a description that they give in the book is basically saying it's a mathematical description of a situation. And we really do use these models to predict change or look at the future of what that situation might hold, or maybe even use it to look at the past of that situation. This is a very vague description because mathematical description could mean a lot of things. Usually that means like a set of equations, but it also could just mean using some numerical idea to describe what's going on in that model. So different models will have different ways to be described, but we'll certainly see different examples of those as the course goes on. The next term to describe is density-independent population, which is now the focus of this first chapter. We actually have a later chapter that will be called density-dependent populations, and we see the difference of how those population models can be described. Why we start with a density-independent population is because they're a little easier to consider and see what they do. And the basics of it is it's just a population that really ignores what its current size is. It doesn't care if the population is large or small, it will keep changing in some constant fashion. So the examples that your book brings up a lot is percentage growth, which is what we're going to be using a lot for our beginning models. We say perhaps a population grows by 5% or some fixed percentage, and that is independent of whether the population is 1 million or maybe even just 2. We just multiply some percentage to that population and it will grow by that much. Or maybe it's shrinking by some amount. It's going down by 3%. So we subtract 3% of the size from the population each time. That does kind of sound like it does depend on the current size, since we are going to be multiplying percentages by the size of the population, but it's because this population is fixed with its percentage growth or shrinkage. That's why we call it independent. If this percentage were to change with the population, that would be something that depends on the population. So let's just jump into the first example of using these models, and we look at the first example of the book on page 2 about modeling grizzly bear population growth. So I encourage you to read the description going on to begin this example, but I'll just give you the basic rundown that they say the population of grizzly bears in Yellowstone Park was 197 bears in 1993. And after that point, they were growing at a rate of 1%. So we want to make a function that represents this population at any given time. So usually with a function, we need some variable. So in this case, we're going to have the variable t. And in this case, we'd like to think of 1993 as our starting year. So if little t represents the number of years after 1993, because we want 1993 to be our base year, then we'll note that t equals 0 does represent the year 1993 itself. And so for instance, another example like t equals 4 will represent the year 1997, or 4 years after 1993. Thus, naming our function p, the function with p of t will be population of grizzly bears after 1993. So this p of t function is what we're really trying to write down some equation or formula to represent it by. But notice, we have something of part of the equation, and that was little r. That's the growth rate of the population. Well, in mathematical terms, usually we write percentages as our decimal form, so we know that the value 0.01 is going to be involved some way in writing this equation down. To help us figure out what this function will look like, we usually go to a flow diagram or some pictorial representation to get an idea of what's really going on. So how these usually go is we have some circle that represents our population that we're trying to figure out. So we're just going to put our p of t function inside here to represent that this is the thing that is being modeled. Now, the changes that are occurring in that model are arrows that either are coming into that circle or outgoing from that circle. Incoming means growth. Outgoing means shrinking. And the only information that we were given in this equation is that the growth rate of the bear population is 1%. So we have at least an arrow coming into this bubble, this population circle, and we know that that should be 1% or 0.01 times, well, whatever the previous population was. Usually by growth rate, it's an annual thing, so it depends on the previous year. So whatever the population is at time t, then we're going to have the population at t minus 1 as the previous year's population. Now let me clean that up a little bit. So how we read this diagram is incoming, again, is addition. We're adding things to the population. The population t inside is what we're trying to figure out, so we write p of t equals something. Now, the other side of the equation is all based on previous year stuff. That's how a lot of these models will be. We take last year's amount and change it in some way, and that will be the new amount. So p of t is equal to something starting of p of t minus 1. We have to take the previous year's population and change it in some way. And that change is exactly what we found here. The arrow coming into it. Arrows coming in mean plus. So we add 0.01 p of t minus 1. So when we started with some population, p of t minus 1, we're going to add a 1% growth to that. So 0.01 p of t minus 1. And there's the cleaned up version of that equation. So again, usually we're going to start with p of t, the thing we're trying to solve for, is always on one side of the equation. And the other side of the equation will always start with the previous iteration, the previous time. T minus 1 in this case is how we're representing that. So population in that previous time, and change to it whatever the flow diagram says. Again, adding because we saw that the growth rate said that we were adding to the population. This equation that we've written down is actually our first discrete dynamical system, or otherwise known as a DDS for short. We are going to be writing a lot of discrete dynamical system equations in this class, and this is going to be our main way of trying to incorporate some formula to represent the population. Now notice, this doesn't give us the population at any time that we want. And by that I mean, if I wanted to know what the population of the grizzly bears was going to be in, say, the year 2020, I can't calculate that immediately. Because notice, this formula, what it relies on, is knowing the previous year. So if I want to know what the population in 2020 is going to be, I need to know the population in 2019. But that means I need to know the population in 2018, and so on and so forth. Notice the only bit of information we were given to start is p of 0, which was 197. So, what can I use this formula for? Well, I can use it to find the population in 1994, 1 year later. So using this base formula, again, I know that p of 0 is 1993, and that was 197. So, if I want to find p of 1, following the formula as it says, that will be p of 1 minus 1, or 0, plus 0.01 times p of 0. Okay, so that means this is 197 plus 0.01 times 197. Just plugging in the values for p of 0 that we know into this formula now. After we do some of the calculations, we find the value to be 198.97. Now, of course, in realistic models, a percentage or decimal value for a bear probably doesn't make much sense, but they in the book just round it to 199 bears, about. This is sometimes the limitations of models. There's some quirks to the numbers that it might give you, but it's still an estimate, might give you a good idea roughly what the value of the population will be. But now that we know this value, we could use this to calculate the next year, 1995, or P of 2. And as we plug in all the information for P of 2, again, as the discrete dynamical system equation told us, we just use the previous year's values, or P of 1. That's our t minus 1 term in this case. And eventually we get down to the population in time 2, which is 1995, is 201 grizzly bears. Again, roughly estimated. Now we are looking at a table of just multiple values from this system calculated out. So we went through 1995, and that's where we got the value P of 2. And so we got about 201 as the value of the population. What this table is doing is just calculating more and more out. And again, to calculate the next year out, we just need the previous year's value through the calculations. So they go through 2002, and they get eventually to about 215 as the grizzly bear population. Calculating out one of these tables by hand is a pain. So that's why we're going to use our big tool, Excel, in this course to help us really do this more efficiently. And that's what the following video will be about. So, see you there.